let's start. Good morning, everybody. I hope that you are doing well. And welcome back to the AIRCAC. Last week in week 7, we moved from simply analyzing an existing data set to actually building our own controlled research environment. We created the synthetic smart campus digital twin, defined the relationship between occupancy, ventilation, CO2, energy, and other variables, and then tested an intervention inside that simulated environment. Today, we are going to one step further. Real research system rarely gives us only one type of information. We may have sensor measurements, images, audio, signals, maintenance notes, and many other sources of at the same time. So today, our question is, how can we combine several different types of data in one research workflow? Does combining them actually improves the results? This is what we mean by multimodal scientific data and sensor fusion. And as always, everything we use today is synthetic. So we are not using the real CSU building, students, employee, camera, or microphone data. So before talking about the fusion, let us understand why we need multiple modalities in the first place. Imagine that we are monitoring one room. A sensor can tell us that CO2 is 9 ppm, for example. That is very precise numerical measurement, but it does not tell us everything about what is happening in the room. An image may give us a spatial information. An audio signal may tell us something about a fan, ventilation, and mechanical conditions. And the maintenance notes may also provide human information that no one of the sensor recorded. So these different work windows into same system. But adding more data does not automatically means better research. Every modality introduces new problems. Synchronization, missing data, quality, provenance, and possibility of leakage. So the principle for today is very simple. More modalities are useful only when they are correctly aligned, quality controlled, and scientifically verified. And sorry. Now we make we make the research problem concrete. Our prediction question is, can we predict whether the new high CO2 event will occur during the next hour? And instead of using only one data source, we give a system 4 views of the same zone and same period. We have sensor information such as recent CO2, occupancy, and ventilation. We have synthetic thermal image representing the occupancy, the density. We'll say that in minutes. Occupancy, the density field. There are no actual people in this image. We have a synthetic HVAC audio signal representing the behavior, the fan behavior, or the possible equipment faults. And finally, we have the synthetic maintenance notes describing events such as filter replacement and fan ventilation. The fan vibration. So the important point is that all 4 modalities describe the same research states from different perspectives. Later, we will test whether combining them improves the prediction or whether no one modality already contains most of the useful information. So as if it's a research topic that we are dealing with, and we does it mean that adding an image can improve the results, or adding the audio can improve the results? Sometimes the experiments prove the combination is true, or is not no need, because when we added one image, we are adding more computation. When we added other sensors or other how to say inputs, we are adding more complexity to the system and more money. So doesn't mean that if the improvement is high, we can have how to say use them, and to improve the if how to say to improve the quality for the human. But if the improvement are so we need to find a way between the money and the accuracy, and based on we can decide. Before we model anything, we need we need a research architecture. So on the left side, we preserve our one row information. We have separate folders for sensors, image, audio, and text. We don't modify these raw files. From this, we process them to extract features, align them, and save our results separately. We can also see the code is separated into source, script, data, metadata, and results. This separation is important because research code should not be one G and Python file, even though for the correction it will be more, how to say, more difficult for people to, even though for experts to control, to correct and to find the exact error. Always we need to separate and to use small scripts and test them separately. The workflow is from the raw data sets, then the alignment, feature extraction, and the fusion. And every past proceeds results should remain traceable to the original file. So even before machine learning, we are already thinking about reproducibility and prevalence. So this is very important to have always reproducible results, or reproducible data sets. This is how to say this time and the location alignment. This is one of the most important problem in multimodal research. It's alignment. Suppose our CO2 sensor measurement comes from building 1, zone 2, and at 10 a.m. The image, audio, and the maintenance now nodes that we combine with it must describe approximately at the same location at the same period or the same time. Otherwise, we may accidentally combine a sensor reading from one room with another image from another room, or an audio recording from another time. The model will still run. Python will not necessarily produce an error, but scientifically the sample is wrong. So that is why exactly we use a shared key based on a building zone and time. So remember, I would say we need to remember this. A program running successfully doesn't mean that the data are correctly aligned. Alignment is a research quality issue, not only a programming issue. So it's very, how to say, if we have an ID is wrong, so the code doesn't, how to say, reflect, but it may a long time provide wrong results and the wrong how to say output, and which make the is. So what I want to say, the programming itself is not the problem here. The research problem is an issue here. So now, one how to say, the modality is aligned. We need to know exactly where every sample came from. This is the purpose of manifest. For every multimodal sample, we record the sample ID, the time step, the building, the zone, the corresponding sensor file, image file, uh, audio file, text file, and the check sounds. We use SHA 256 checksum, so that is later we can verify that the file has not unexpectedly changed. So this is SHA 250 is how to say is secure a cybersecurity method. We use it to it's used in cybersecurity a lot. So it's well-known method that we use in cybersecurity, but here we are using it to check the modality. So we also record whether the modality is available, the random seed, and the review status. So if somebody asks us 6 months later, we did not, how to say, we did these results come, where did these results come from? So it is we should be able to trace the proceed, row back, and to extract the source file. So this is very important for long-term research issue. So after even though for I will write, for example, one paper after 3 months, 4 months. If I don't do that now, I know that it's time a little bit time consuming. But if we don't do it now, I'm talking about myself. After 3 months, I don't find, even though I don't remember the name of the folder. So we need to be organized from the beginning. That everything is it's how to say well written, well documented. Then after 1 year, 2 years, we can have how to say this how to say go to this folder and go to this website and find everything there. And it's very important to double check always the traceability. So this is how to say especially important in multimodal research, because we are managing many different files simultaneously. So this is very important, not only for simple thing, but for multimodal. It's an obligation. It's mandatory to have this traceability, because even though you instant and you know the multimodal, you don't know exactly what's going on. Here it's simple from the image quality. Now let's examine the image modality. These are synthetic time thermal style occupancy map. They are not real camera imaged, and they don't show identified people. So we don't have any people here or anything. Just it's synthetic data set that we generated to test our model. The brightness region represent the higher simultaneous occupancy density. Instead of immediately giving raw pixels to complex black box network, we first extract samples, interpretable features. For example, mean intensity, contrast, blur, score, saturation fraction, and the edge density. These features serve as two purposes. First, they help us characterize the image. Second, some of them help us to detect the quality of the problem or the quality problems. For example, if an image is extremely blurred and saturated, we should know that before using it for modeling. So again, it is the order is quality first, modeling second. This is very important. So, for example, here it's blurred, but here it's more clear. So we need first to know that this is very important. We need to check the quality first before going to how to say to the modeling, or to talk about the model. So the data set is more important than the model itself, if I can say it like that. The second media modality is audio, where the generated here we generate the synthetic HVAC signals. For example, the fan frequency can change with the ventilation, and the equipment fault can introduce another frequency component. So here we are studying the frequency of the vibration produced by the ventilation. And based on the if the ventilation has faults, it will generate other sound. Other sound means other frequencies. So we are using Fourier transform here. We are not using the time. This image represents 2D. How to say? How to say discrete Fourier transform. That is not, we can move it later on to wavelet, but it's not wavelet, it's only the time versus the frequency. And we can see here that, for example, here we have two high frequencies here, we have one frequency here, and we have one frequency here. It's clear, it's not one frequency, but one clear frequency over the time. It's give us the information that what's going on before I would say going to the model or the multi-model. We can visualize the signal as a waveform, but spectrogram is particularly useful because it shows how the frequency content change over time. From the audio, we calculate the features such as RMS amplitude, spectral centroid, dominant frequency, and clipping fraction. So we also calculate the signal noise ratio proxy SNR. We want also to emphasize the word proxy. It is not the calibrated physical acoustic SNR measurement. The important scientific lesson is the same as with the image. We convert the modality into interpretable measurement and quality indicator before combining it with other data. What we are, let's say, I will give you one example. So let's say the noise is how to say embedded with convolution in time. Let's say have for example the signal is the real signal convolution with the noise. If we want to extract the noise simply, it's not easy in time. When we convert it to Fourier transform, we will have the convolution will be converted to multiplication. So it's simple to extract the noise. It's only to divide the whole signal by the how to say the noise signal and remove the noise, because it will be a simple multiplication, and we can convert it to simple division. But in time we cannot manipulate convolution, because convolution is embedded inside the signal itself. Is not addition, is not additional this how to say noise. This is therefore we are going to have, this is our job here, to provide the maximum, how to say, the better interpretable how to say image or signal, 2D signal like this to the network. At least we understand how we can interpret, because if we put it only as a noise in time, it's very difficult to understand what's going on or to have the frequencies added in the system. I would say as an input of or getting the vibration faults from timing issue. So this is important. Here we are saying the text notes and structured event extraction. So our third additional modality is the text. Imagine that the technician write ventilation fan vibration detected. This is the technician wrote this. We can convert this into a structured flag indicating that a fan event or filter replacement completed. This is another node that can combine the filter change event. But notice something important. Most periods have no maintenance nodes. That doesn't mean that nothing happened. if it only means that no note was recorded. So text is sparse by design. This is good example of why missing information has a meaning. Missing text should not automatically be interpreted as negative events, because if there is no maintenance, for example, for this period, does it mean that we don't the fund is not faulty? So we need this is, we can call it as not mandatory input. It can help, but its absence doesn't mean that something wrong. This is what we want to say. Later, when we compare the modalities, we will see that the text alone is actually a relatively weak predictor in the particular scientific experiment, and that is okay. Negative results are also research results. So also it doesn't mean always we need to have positive results. I reject the results, not only for this week, for maybe for the next weeks when we move forward, we can have rejected the results, and it's negative results. Also, we can sometimes we can publish that we are advising people to don't use this model. So the missing modalities and synchronization errors. Now let's imagine that this system outside an ideal laboratory. An image may be unavailable. An audio clip may arrive late. A maintenance note never be written. A sensor window may contain missing readings because of fault. This is normal in multi-model systems. Therefore, we should not build a model that works only when every input is perfect. The need to understand how the system behaves when one model disappears. Later today, we will deliberately remove modalities and measure how much model performance changes. This is called missing modality stress test, or sometimes you can call it an ablation study. It tells us which modalities the model truly depends on, and which modalities are not very dependent. And this, it will help us to minimize the cost in time and in money. The uni model, or the early fusion and the late fusion, because these models cannot be, how to say, go to depend, I would say, to all of them to go to the output, to give us the output. They need to be combined. When we combine, we can have a early fusion or late fusion based on the model. There is several ways to combine the modalities. The first is the uni model, or unimodel modeling. We build one model using sensor only, another using the image feature only, another using the audio, and another use the text. This gives us our baseline. The second approach is early fusion. Here we concatenate all the features into one large feature vector and train one model. The disadvantage of is that combine can become sensitive to missing inputs. This is the, I would say, the early fusion is this is the weakness of the early fusion. And the third approach is late fusion. We build the model, we build the separate models and combine their final probabilities. This is modular and sometimes more robust, but it can miss intersection between modalities. There is no universal winner. That is why today we don't assume fusion is better. We test it. So this is very, very important to understand that maybe sometimes the late fusion can work better than early fusion. Let's say, for example, Groot in VLA model for NVIDIA, they are using late fusion. The other models are using early fusion, and it's not there is no criteria that suppose or confirm that one model is how to say is preferable. We need to test and to test it and apply it to our system, apply it all, and check which is the best. This is I would say a part of the research. Here we have the high-level multimodal fusion workflow. The figure summarizes the on-tier week 8 architecture. Let's start from the left. From the left side, we have our four information sensor stream, thermal image, HVAC, audio, and maintenance nodes. Each modality first passes through its own quality control and feature extraction stage. Then we align everything into one zone, our feature table. That's alignment step is critical because every row must describe the same zone and time. From there, we can test three strategies: early, how to say, uni model, early fusion, and how to say late fusion. So we test them. So means that at the end we will have only one. Maybe the I would say, just I'm saying, maybe the late fusion is better than, and we can use the late fusion. If for another model you are using for another model, you can find maybe the early fusion is better. So we need to test all of them. Here, why I'm saying like that, this figure doesn't mean that we will use all of them. We will use only one after testing all of them. So in reality, we have the four sensors. The second block quality check is same. Alignment with the zone or it's also feature table is same. But after that, we can go to only A or B or C. Then the predicted next year high CO2 onset risk. All this, I would say, so let's how to say all this approach finally produce the same type of the output, the predicted risk as I explained. So we need to remember or if you remember only one architecture from today, remember this picture: multiple sources, quality check and feature, alignment, fusion strategy, and prediction. This is what we need to remember, maybe for other features, because we are not targeting. This is just a sample or an example, but you can use it to your research. The strategy is similar. So one important thing is the data leakage in multimodal research. Before we train anything, we need to make sure that we are not cheating. There are two major leakage risk here. First, future information leakage. We are predicting the next hour, so we cannot use the information from the future as an input. This is very important. Every feature must stop at the decision time. Second, related sample leakage. Samples from the same zone at adjustment hour are strongly related. If we randomly shuffle everything, very similar observation may appear in both training and testing data. That can make the results look much better than it really is. So we need so what we respect time and the related samples when we constructing the evaluation. The simple rule is, if information would not be available when making the real prediction, it cannot be the future set. This is very important. So it's not how to say use the same data and use the same training data and or shuffle the data and divide it by 60, for example, 70 for training and 34 for validation, or for 15 for validation and 15% for testing, maybe the other, I would say, is not the right way to shuffle. So the shuffling itself, even though it's right to how to say, it's scientifically correct, but it's not how to say, if you can avoid it and make the model more accurate in the future, use this data set and apply to unseen data set in the training. This is what we want to achieve. So before starting, how to say, the demonstration, I want to show where everything is. The complete 8 package is available on GitHub repository. You'll find the codes, scripts, rows, synthetic data, process data set, metadata set, tables, figures, and logs. There are two ways to run the workflow. The easiest way is simply to execute the run week 8.batch. .bat, sorry, it contains the executable that runs the complete pipeline. Or if you want to instant every stage, you can execute the 7 scripts manually, and it's very, I would say, it's both are the same. If you it's based on your how to say, your thinking. If you are, how to say, you want to see the results and then apply it later on, it's fine. If or you want to instant now, also it's fine. The work, how to say, they follow the exact research workflow we have discussed. Generate the multi-model data, build the manifest, perform the quality control, extract the future, train the ONI models, train the fusion models, and finally run the missing modalities stress test. After today's session, we can reproduce everything ourselves. So from the repository. Let's say, for example, now let's us move for how to say, for the next step. For the first, I would say, demo, we will generate our multi-model files, construct the manifest, and perform the quality control. We will I ran this code before. Our expected how to say results, it will be 16 representative multi-model samples containing sensors, image, audio, and how to say, sensors, also the text information, the audio, the image, and so on. We should also obtain our manifest checksum, image quality table, audio quality table, thermal maps, spectrograms, the waveforms, and the modality availability figure. So if we switch to, how to say, to the Visual Studio, we can only run Python scripts, Python space scripts, one generate model, multi-model data sets here. So this is what we want to run. This is the three I would say comments that we will create here. So only we need to apply this to generate the data, and to build the model and the manifest. And as we did before in the previous weeks, simple, only apply, how to say, start the Visual Studio and open the folder, select the folder that you are working on, and that's it. So download the GitHub folder, zip file, unzip it, and put it in the how to say, folder, how to say, you are, or the location that you are working on. Open my Visual Studio, and that's it, and run it. If you want to instant any code, just ask Copilot to explain the code, or just follow these three lines to how to say, to have the results. These results are, how to say, we already have them from the when we run the code. and as you can see here, the modality availability text is dispersed by design. So synthetic, we do that in purpose. So we don't sometimes, as I said, we don't need to have the it's not we don't need, but sometimes we don't have the text from the maintenance. They don't check every day or every hour the quality. We have this note; it's constant. So therefore you find the number of samples that we are using here. So it's just demonstration here. Is not we don't generate a lot of samples, but we generate only some samples to test our code. 60 samples is not big for big models. If we want more, I would say, accurate or more generalized model, we need for sure we need a lot of data set. This is also very important. So second, we need to align the, I would say, as we said, align features ensuring the uni model. Also, it's very important to have it. We have how to say the alignments are how to say the uni model test give us that the sensor 99%. The other one, the audio 96%. This is separate model that we train and we align the models. We have how to say 14,380 aligned samples. We have 27 features and the balance the next our target target. We have the I would say also the how to say the CO2, the other sensors. So if we want to explain what are the features that we have 9 sensors plus 5 images and 5 audio and 8 text. This is from where we get the features. It's not the image is the feature of the image. So we need to also to understand how to say understand that it's very important to we need now to compare the results of the uni model versus the fusion, and we have also late and early fusion. Are the late and the early fusion give similar how to say almost similar features, but we can see the early fusion give better scores, and the sensor only give also better scores which provide how to say uh, let's say similar results. So early fusion and sensor only gives how to say almost same results. The text only gives the worst results. So it's not it doesn't mean it's not necessarily, but when we use it alone, it provide us low result, low accuracy. If we use only the text to model, it gives us the low accuracy. So it is how to say the model that concentrates heavily on sensor modality. So it is relatively robust and to lose in the weaker modalities, but much more reliable to losing the dominant sensor information. This is exactly why missing modalities text is useful, but using the multimodal system, we should know which input can disappear safely and which input is critical. This is very important to understand. Better, how to say, better simulation fusion would not prove, how to say, better real world fusion. This is also an important information. Here, when we drop the sensors, when we drop one by one, or we drop all the sensors, when we drop one by one modality, we can say that, how to say, the drop sensors affect how to say the modality, and this is stress test that we when something is missing. When something is missing, I would say it I would say provide how the model will react to this missing data set. So we can find here that robust to losing weak modalities, vulnerable to losing the dominant one. Now with this before the development, so we need to know this all of this before developing any model. So the responsible interpretation and privacy and provenance before closing, there are three modalities I want to remember. First, privacy. Our thermal maps are synthetic and non-identifying. If you work with the real imagery, audio, and human data privacy constants, IRB and institutional requirement became very important. So especially in thermal, it's very, even though in synthetic is a little bit tricky here, because it's not it's not allowed to everybody. We need to identify everything that we are using, not only, but it's similar to the image, RGB image. So we don't even though we see only the thermal things. It's also our responsibility to have this to have the approvals before using that. This is very important. Second, it's provenance. Every proceed result should remain traceable to its original source. If we cannot explain where results come from, it becomes difficult to defend that results scientifically. And third, honesty. Today, Fusion did not beat CINSER-only model, as we saw here. So as I explained here, the CINSER only give us almost same results as early Fusion. So why we are using early Fusion if we can use only the the sensors that we have? So if we never force the model to provide you good results, force go to the right things, and always we need to be honest with ourselves. These are results. These are good results. Means that we are advising people, don't use just I'm saying, don't use other sensors, or don't use early or late fusion. But if we have the choice to use early fusion and late fusion, we advise with this plot or this bar chart, give us the the clear that the early fusion is much better than the late fusion. So we report that exactly how exactly as it's happened. So no need to explain things that out of the reality. And all of these results are synthetic. We are not claiming real world performance or real world causality or development readiness. So also this is, we need to mention it in this session. So for our own practice, if you can think about small multimodal research problems that you can completely trace, we should have a manifest with checksums. We should have synthetic or approved low risk modalities. We should create a quality control report, then align the modalities into a common feature table, build at least the individual modality baseline and one fusion approach. Finally, remove one modality and see what's happened. The objective is not to create the biggest possible model. The objective is to create a multi-model workflow that instant and can defend. And remember, all of the week 8 codes and examples and are available in the GitHub repository, and so we can reproduce the workflow and adapt them, how to say, accordingly. But also we need a little bit computing system to run, because the multi models are not how to say this. Why I didn't show here in laptop, but we can run them. If you have a workstation, you can run them in workstations, or if you don't have workstation, you can use Kaggle. You have 40 hours for free each week, and or you can use how to say collab of Google, that also it gives us 12 hours a day, based on availability of the GPUs that they are giving for free, and other we can find with also with Amazon. We can find with APIs that you can run the codes, and you can use the GPUs for free. But this is not issue. The issue is not the issue, but the most important thing is the model itself, the data that you are using, and the use of the AI is also are important in our case. And how to say, the always when we need to propose something, we need first to have the review what is going on in that time, in the actual time. Then we need to, I would say, to start and sending or start reproducing results for one paper. Then we can how to say start how to say thinking how we can resolve its limitation and the limitation of their model by introducing new techniques or new models if we are working in models. But if we are working, for example, for another area, it's different, and based on your area, you can define the, how to say, the approach that you are using. Sometimes we don't need, even though we don't need sensors, if you are working for simulation based, I would say, technique, that it doesn't need even though simulation. So what I mean, if you are working on pure simulation models, mathematical models, you are not, I'd say, you don't need a sensor in this case. So to summarize today's week, different models give us different views of the same research system. Before the fusion, we need to align. We need alignment to quality control and the provenance. This is it's a mandatory step that we need to do it before proposing fusion. We must control the leakage and respect the structure of the data set that we are using. And most importantly, fusion must be tested, not assumed to be better. So always we need to, how to say, to prove something before assume, because we can say that using the audio and the video can improve the results. Did we test it? If yes, we can say it, provide us the results. If you don't test it, we need to never assume something is working before testing it. As we proved today that the using of fusion is not a good idea to use the fusion. I would say, yeah, as I said, in our experiment, fusion did not outperform the strongest sensor modality, and that is important and honest results. Next week, in week 9, we'll take the strongest predictive signal forward and ask much more rigorous question. Can we turn a good model score into defensible scientific evidence? We will work on leakage, auditing, calibration, uncertainty intervals, and subgroup error analysis. And thank you very much for everybody. And I will, if you don't have any question, we'll meet or we'll see in week 9.
Hello, I have one quick question. How do you know when you've analyzed enough data to know that your models are producing, I don't know, accurate results?
If if you understand very well your question, Professor Kim, that let's say, for example, we are using the images and the
Hmm.
audio and the modalities, how we can prove that these are good or bad, that provide good results or bad results.
How do you know you have enough measurements or incidents? How many, data points? I know you have to, they're collected at different times, and so you have to align the times. But how do you know, maybe you have data for 1 day versus data for 15 days? How do you know how much data you need to know that your results when you're doing a fusion and trying to test whether which case produces the most faithful results? How do you know from a data standpoint that you have enough?
No, we cannot have for data itself. We cannot without testing using the model. We cannot say. But in general, using more data sets provides better generalized model. The parameters that we will have, only the parameters that the metrics that we will have is based on the use case. Let's say, for example, that I am using the prediction, the RMSE matrix is we can use it, or another map matrix MAPPE, we can use them, but based on the model. So let's say you have only 1 day and you want to use these data sets to test your model. You can have the results, but doesn't mean that for day 2 it will provide you better results. If I understand how to say your question very well, in general, more data sets gives us to train the model, give us better results in testing, because we are feeding the model by the maximum information that he can learn its weights to give us the most accurate output. If now you have 15 days, if the 15 days, the next 15 days are similar, have similar data sets to the first day, if I can say like that, the most probable result that you will have is similar to the first day, because it's every day you have the same results. If the data set changes every day, means that you need to feed the model for training for with the maximum data that you can.
Okay. But you said you were using synthetic data, so you generated a fake
Yeah,
data set. So how do
it's
you
not.
know how much synthetic data to generate?
No. The first, it's not fake. It's not fake data sets. We can say simulate the realistic data sets, because we are generating that from digital twin. So it's not first is not synthetic doesn't mean fake. Synthetic means that results generated based on the features of the realistic data sets. This is what we mean by synthetic. Synthetic doesn't mean how to say, even though generated by code, but they how to say, they act to the realistic data set. Except if you don't have these features in your synthetic data set, it's useless to use your data set. Even though realistic data set can, for example, if I can say synthetic data set of the room, means that my model, my mathematical model, and I remember your question last week. I forgot to tell you that we can have I have already a paper in GitHub in archive. I will share it with you maybe next week, or I don't know. But the idea is the digital twin is the digitalization of the model that can, if we give the same inputs that we are providing to the real system, it will give us, it will react, the model react to, how to say, to these inputs as if it is real. We need also to distinguish between digital twin and neural networks based model. Neural based model is use the data set to learn and as our brains they teach us from the beginning that this color is red, this color is black, this color is white, and so on. They are teaching our ways in the brain. This is another technique, and we are not using neural networks to produce the digital twin. It's not digital twin, it's model based technique. But in digital twin we are using analytic and deterministic how to say equation that they represent the real system. This is first, and based on we generate how to say the synthetic data set. The synthetic data set we can generate it using simulation, using for example Isaac Sim, using Unreal Engine, using Carla softwares. We have a lot of softwares that we can generate synthetic data set, simulated data set. In our case, we are using digital twin to generate the synthetic data set. Due to the, I would say, why I choose 60 just as a demo example. But if you are using your data set in reality, I generate 6, I would say, but in reality, I have more than 67,000 data set I used. So here I use only the data set. I pick some samples just to test the model, test the modalities, and to save time. And I will be honest, I would say here, to prepare for this 1 hour, I take 2 days, exactly 2 days to prepare. It's not coming out say for 1 hour, and I'm honest here to tell you that the amount of work to provide this 1 hour and all the hours before, it takes for me more than 16 hours to prepare only that. And if I, for example, use more than, if I use 14,000 data sets, I cannot train the model in one week. It's not in only training. So this is the why I use only 60. If I can reply to your question, why I use only 60 here, and just to test and to have proof of concept for because my goal here is not to propose a research level techniques, or is to help people how they can start their research with how to say their own ideas. So this is the idea. This is why I said in the model, this model can be used how to say can be used for CO2 and the prediction thermal, but you can use it if you, for example, you have another sensor here. Let's say, for example, you choose to use it in positioning. You can use this as Professor Ayesh is using in Edge AI. He can use how to say CO2, how to say CO2. He can use GPS. He can use IMU. He can use the image comes from the camera from the car. He can use the how to say, rather than using the audio here, he can use the wheel vibration sensors. He can use the control. Go to the left, go to the right, rather than maintenance nodes. So you got the idea, Professor Kim. So the idea of these courses is not to provide the research, I would say, topics, or to defend. Just it's I would say to give the maximum information to people that they can start as a starting point to people that they can start their research safely, because now the AI can do things that we cannot how say even though imagine, but we need also to be careful for things that that we will give to people, especially in research. We need to be sure to that everything is aligned first with ourselves, then align the data set that you are using for your research. I hope that I clarified this point, Professor Kim.
Oh, you did. Thank you.
So thank you very much, and I hope to see you next week. And bye-bye.
Thank you. Bye.